All right, so chapter 3, we're going to learn huge skills today. So types of bonding, naming compounds, and empirical and molecular formula. Those are the big three for today. So let's jump right into it. There are two types of chemical bonds. The first is the ionic bond, which has a positive and a negative charge. And in the next slide, I'll show you there's some GIFs that really accurately represent what's going on in an ionic bond. So it's electrostatic, but electrostatic, I don't like using that term because since it is, but there's a lot of things in chemistry that are electrostatic. Hydrogen bonds are electrostatic. Really anything, even very weak van der Waals bonds are temporary hydrostatic or electrostatic. But regardless, it is formed by oppositely charged ions, a positive and a negative, and usually, well, definitely, the metal loses an electron or one or more electrons, gives it to the nonmetal, which then gives the nonmetal a negative charge, gives the metal a positive charge. And that charge induction leads them together. So you can see that here in the picture on the left, where it shows ionic bond with sodium. So sodium has one of these electrons. So sodium, I'll show you a periodic table in a couple of slides, has one valence electron. So sodium likes to get rid of that one valence electron in order to get to its inner valence shell of 8. So once it loses that electron, what's nearby? Chlorine. So chlorine is the opposite of sodium. It wants to really highly gain an electron. It's what we call a high electron affinity. So affinity means a liking for something. So chlorine has a high electron affinity. Chlorine walks in the bar, yo, who's got an electron? Sodium's like, I have an electron, I don't want it. So it's a very seamless transition, a very seamless transfer from sodium's electron to chlorine. Once that electron is transferred to chlorine, this action induces their charge. So initially, every atom's neutral. Once sodium gets rid of that electron, it loses a negative, therefore becomes positive, as the bottom picture shows. And then the chlorine becomes negative by gaining the electron that sodium lost. So that is what creates the ionic bond. It's the transfer which induces the charge creation of the cation positive, the anion negative. And those are other two terms to know as well. Cation is a positive ion and the anion is a negative ion. So you usually have positively charged metal cation, negatively charged non-metal anion. That's usually a thing. Yeah. Okay. Any questions on ionic bond? No? Okay. Next one is covalent bond. So covalent bond's they're easier to name, definitely. And that happens when you share electrons. So who's ever seen 21 Jump Street in this room, right? With Channing Tatum when they switch places and they got the wrong names and he's ended up taking a chemistry class. So he's he talks to the nerds, he's like, what do you guys learn in this school about covalent bonds? And then he ends up learning what a covalent bond is. So it's the sharing of electrons between two atoms. And usually for covalent bonds, it's non-metals are partaking in these covalent bonds. So that is that's one very important thing when we're naming. So the way we're going to learn naming these bonds is we're going to learn ionics first, then we're going to learn covalents. And it may seem pretty easy at first, but once I start mixing them together and giving you, let's say, 10 questions, or I'm going to post a worksheet on Canvas with like 30 or so examples. But once they're all mixed together, you lose track of what rules to use because we're going to learn different sets of rules. So the way to tell yourself which rules to use is by first identifying what kind of compound it is, ionic or covalent, or an acid, which that's another type we're going to learn today. So, well, acids tend to be covalent, but and bases tend to be ionic, but we'll learn they have a different naming scheme as well. So the first thing is you always tell if it's ionic or covalent, and then you can use that naming scheme. And covalent is usually between two or more nonmetals. You can see this is hydrogen peroxide on the right over here. Move this out of the way. Yeah, and hydrogen peroxide has a hydrogen covalently bonded to an oxygen, which is covalently bonded to another oxygen and another hydrogen. And then the ionic bond is always between, or usually between, a metal positive and a non-metal negative. Okay, moving on. So here's the GIF. I think they both, no. Why isn't the right one working? No, whatever. Oh yeah, so you can see on the left the sodium giving that electron to the chlorine, creating the charges. That charge, positive charge in the sodium, negative charge in the chlorine, creates the electrostatic attraction. That GIF should work. No, whatever. All right. Anyway, this is the trend for ionic charge you guys should know. So I'm going to go over it right now. This is the best one I could find. Oh, as it goes away. This is the best one I could find. It kind of encompasses everything. So you have group 1A. Group 1A is over here where hydrogen is. They have a +1 charge when they become ions. And the reason why is because that 1A, also means one valence electron. When they have one valence electron, very similar to sodium, it's going to get rid of, or want to get rid of, that valence electron. And once it does, it will have an inner shell of its electrons. We'll learn more about electrons in chapter 8 and 9, but basically it has an inner shell of valence electrons that is satisfied and completely filled up. So that means it's happy at that level, and it's more likely to get rid of that one electron for group 1A. Does that make sense? Okay, good. Because the rest of the periodic table works very similar. Now, 2A is exactly the same thing, but instead of one valence electron, it has two. So beryllium is weird. Beryllium actually likes to partake in covalent bonds, right? Beryllium dichloride, for example. But you're not going to see beryllium for ionic usually. But magnesium, calcium, strontium, barium, and even radium sometimes you'll see as +2. So you'll see those are very frequent ones. I'd say magnesium, calcium, strontium, and barium are the main ionic +2 alkaline earth metals that you're going to see. And then, so you have the middle. The middle is kind of blued out, right? So anybody know why the middle is blued out? Yeah.
Well, the metals are wacky and they can be positive or negative.
Not negative, but they are wacky. So I like that answer. So the metals are wacky. And what that means is they're called the transition metals, right? So they have a transitional charge. You don't really know what they are. They could be +1, +2, +3, +4. They have different charge states for most of them. Then you have silver, cadmium, zinc, which just don't follow rules at all. But for most of them, like iron can only be +2 and +3. Chromium could be +2 and +3. Yeah, so there's multiple charge states for a lot of the ones that are blued out. And also, Josh made a good point. I think that was Josh. Yes, covalent. So the ones on the right that are blued out, silicon, a lot of these metalloids, a lot of them partake in covalent bonds. So, and they don't take part in ionic bonds at all. But also they don't really have a definitive state, a plus or a minus for a state. Also to make that point, the nonmetals in the top right here, they also partake in covalent bonds, but when they can also take part in ionic bonds by being an anion, and they have charges as well, which we'll get to in a second. So that part's blanked out. Then we'll skip the zinc, cadmium, and silver for now. We'll go over to group 3A. So group 3A is right here with aluminum and gallium, right? And not including boron and not including the other ones, just aluminum and gallium. They have a +3 charge. So it's the same principle as group 1A and 2A, but for aluminum and gallium, they have 3 valence electrons, like to get rid of those 3, and they get a 3+ charge. So that's that, yeah. Okay, any questions on those? Those are the big 3 groups. Group 1A +1, 2A +2, 3A +3, at least for the cations, the positive charge ones. Good? All right, cool. And if not, you can listen to this again. All right. So then you have some exceptions that are in the middle. You have zinc, cadmium, and silver. Now, luckily, it forms a little micro trend where it goes, if you look at it from hydrogen, it goes +1, +2, +1, +2, +3. There's like a little micro trend there. But just focus on +1, group 1A, +2, group 2A, +3, aluminum, gallium. The reason why zinc, cadmium, and silver are here is because, again, they have nowhere else to put them. Because they're kind of act like transition metals. They're not the other ones, so I guess we'll throw them in the middle, whatever, even though they have one charge state, whatever. It's not perfect. So zinc is going to be a +2, and it's always going to be a +2. And same thing for cadmium, same thing and silver is going to be +1. These three are actually important when they show up in naming. Because something we're going to learn is that if any of the metals, when we're naming a compound, are the metals that are shown here, group 1A, 2A, and then these 6, these 5 over here. If those metals show up, we don't have to use what we call Roman numerals, or what we call, everyone calls them Roman numerals. So we don't have to use Roman numerals when it comes to naming the metal. For the other ones that are blued out, we have to use another rule to actually tell the reader what the charge is. Because for, like I said, for iron, the charge could be +2 or +3. So who's to tell them, who's to say it is? It's your job as the person writing the name of the compound to actually write iron 2, iron 3. And we're going to write those 2 and 3 in Roman numeral form. So the ones that we know the charge of by looking at this trend list, we don't have to write that for, because to the educated chemistry reader, they already have their charge. We already know their charge. It's definitive, and it's only one of these charges, +1, +2, or +3. So that comes into play later. Okay, so next is the anions. So the anions are all the way to the right of the periodic table. Now, unlike the cations, they do not lose electrons. They're going to gain electrons from the metal, and until they have 8. So let's start from the halogen. I'll start from noble gases. The noble gases are very noble. Like we went over noble gases. Big hair. Whatever. So they don't like to react with anything. They don't have a charge, and they don't partake in ionic bonds. All right, and it's the other elements of the other nonmetals' goal to achieve their number of valence electrons. So we'll use the halogens as an example. The halogens, you have fluorine, chlorine, bromine, iodine. They all have a -1 charge. The reason is because they have a very high electron affinity. Because they're in 7A, they have 7 valence electrons. 7 valence electrons is extremely close to 8. So they are almost at the end of the race, and they see the finish line, and they're sprinting to the finish line. They're doing that last push. So they are looking for that last electron in order to get to their happy place, their happy 8 valence electrons. That's why they only tend to gain 1. And once they gain that 1, they go from neutral to -1 charge. So that's how that works. Any questions on how that works? Or why that works? So all those 7A's are -1, is basically what I said. If you know that, you're good. Okay. So then the same thing applies for 6A and 5A. But it's limited. It's not all of them. So for 6A, I would say oxygen and sulfur are the main 2. Selenium, yeah, I heard selenium could break some rules. But oxygen and sulfur are the main 2, that when they're at ionic, they take a -2 charge. Because they're in 6A. That means they have 6 valence electrons. They want to gain 2 to get to 8. So then once they gain those 2, they become -2. And then the same thing is true for nitrogen and phosphorus, where they have 5 valence electrons. They're in 5A. They want to gain 3 more. Once they gain those 3 more, they become -3. So those are the trends that you should know. All right, any questions on those? No? Okay. All right, so now let's go right into naming. So we're going to name simple ionic compounds first. So we call them binary ionic compounds. Now, the best way that I teach naming, or the easiest way to understand it, is just go by examples that we know, right? For covalent bonds, I'm going to use carbon dioxide, carbon monoxide. For ionic, sodium chloride. I say it every 10 minutes, I say sodium chloride in this class. So how do we name it? So it's NaCl. Sodium is the first word. Na is sodium, and that's the metal name. That's exactly the rule. So the first rule is you write the name of the cation first of that element. If it's calcium, sodium, potassium, magnesium, you write that name. The next step, you see chloride. And then if you look at the periodic table, the element Cl is what? It's chlorine, right? Not chloride. So there's something different there. And if you guess that, you're right. And that difference is the ending. So you take the periodic table name of the second element, the anion, and instead of making it an IDE ending, or INE, or whatever ending it is, you're taking off that last syllable and you're turning it into an IDE, IDE. And then we see that in the next, yeah. So you change it to an I. So chlorine becomes chloride. Sulfur is a weird one. Sulfur becomes sulfide, not sulfuride. What does oxygen become? Oxide, yeah, not oxide. But what about nitrogen? Good, nitride, awesome, yeah. I see some weird ones, nitroide and stuff like that. But a rule for chemistry naming is if it flows, it's probably right. That's probably, yeah, because think about it. People invented these naming schemes. They want it to sound good, right? So phosphorus is not phosphoride, phosphide. Sounds a lot better. Okay, so let's name them. What's the first one here? CAS. Ca is what? Calcium. And S is? No, not sulfur. I heard sulfide. I heard someone say it. Did you say sulfide? Oh, you said, okay, cool. So collectively we got it. So it is, and also on the chat, two people seem to get it. Perfect. Sulfur. You're a little late to the party there, but yeah, sulfur. Good job. All right, so it would be calcium sulfide. So you take sulfur, which is the last element, and you change the last syllable to IDE. You take sulfur, which is the last element, and you change the last. Oh, that's my echoing. Please mute your microphones. I hate hearing my own voice. I don't know how you guys deal with me. Okay, next one, KF.
Potassium fluoride.
Perfect, potassium fluoride. And what did you say? Potassium, awesome, good. What about next one, MgO? Good, awesome. What about MgCl2? If I were to say that, so MgCl2.
Magnesium chloride.
Yes, magnesium chloride. So I'll write this one down. So if I say MgCl, MgCl2. There's a button on the side of the pen, and I clicked it, and it makes it weird. So MgCl2. So I was hoping one of you would say, oh, it's magnesium dichloride. Yeah, someone was, you were thinking it. Yeah, you were thinking it, yeah. So that's not right, because something that's important about ionic compounds is they never use these prefixes. We know the prefixes because we've heard, oh, carbon dioxide, oh, carbon monoxide. And we've seen them on medicine bottles and things like different di, tri, tetra, whatever. We've seen those. So we think, oh, we're naming compounds. They're somewhere. But that's true, but only for covalent, not ionic. So I'll tell you why in a second. This is magnesium, Magnesium chloride, not magnesium dichloride. So magnesium chloride. So the reason why in ionic bonds we never ever use prefixes is because of math. It's because we know that an ionic bond has a specific rule. And that rule is that the positive charges have to balance out the minus charges, the negative charges. And that's true for magnesium chloride. And there's only one magnesium chloride. Because magnesium, as we learned, Mg is 2 plus. And Cl, we learned, chlorine is -1. So the only way for magnesium to cancel out with chlorine is if you have 2 chloride anions. Because you have -1 and -2. And that would cancel out with +2. So ionic bonds only have one way of working out. That's why there's no need for prefixes. Whereas carbon and oxygen, there's 2 compounds of carbon and oxygen right now. One of them can kill you, one of them you need to live. So if you just say carbon oxide, that's not telling anybody what you can kill somebody with that. You don't know, they don't know what you're talking about. That's important for covalence because they don't follow mathematical rules based on charges. Their interactions are different. Their interactions are based on sharing of electrons, not necessarily charges. So you would need to do the prefixes. You'd have mono, so carbon monoxide, carbon dioxide. So that's where those would come in. That's for covalent. Does that make sense? So for ionics, it's very math-based. The positives need to equal the negatives. Oh, there we go. Look at that. Don't use prefixes for ionics. I was ahead of myself. What would Na2S be? Na, and it's a sub 2. Then it's Na sub 2S.
Sodium sulfide.
Good. Sodium sulfide. Good. It would be 2. So each Na is +1. There's 2 of them. And then sulfide is -2. So there'd be only 1 of them. 2 sodiums to 1 sulfide makes sodium sulfide. Good job. Okay. So moving on. What time is it? 7. We'll take a break after covalent. We'll take a break, or after, I think acid comes next, right? Oh, yeah. We'll take a break after acid. Okay, so next. When you have these transition metals, the ones that you do not know their charge, this is how to write their charge. So you're going to do the same thing. You're going to name the cation first. So you name the metal, right? Let's do the first one as an example. Fe. Fe is iron. So we're going to put iron. Then you're going to modify the name of the cation now. So you're going to have an iron something. And that something includes the charge of each metal ion as a Roman numeral. So what that means is you're going to have to figure out the charge of each metal ion. And there's an easy way to do that. And then the next part, the last part's the same. With the chlorine, in this case it's Cl, it would be chlorine, so it would just be chloride. Now, can anyone tell me how or what the charge is of this iron in FeCl3?
3 plus.
Good. 3 plus, good all around. And the reason why is because you know your Cl already. You can look at the periodic table, you know your trend, you know that Cl is -1, and you know there's 3 of them. So if there's 3 minuses, there has to be +3 on the other end. And that other end is just Fe. So it has to be iron 3 chloride. That would be your answer. And it would look like this. It would look like that. Iron 3 chloride. Oh, you saw iron 2 chloride. Okay, cool. The next one would be iron 2 chloride, as you just saw, because you have Cl2 now. So this means the charge of iron now changes because there's only 2 Cls. Okay, who could tell me the next one? Cu2O.
Cu's copper.
Yeah, Cu's copper, yes. I'll give you a hint. The ending is oxide.
Copper 1 oxide.
Good, good. So, all right, we're still learning, yeah, but good. Copper 1 oxide. Good. I heard some people say copper oxide, but the reason why it's copper 1 oxide is because in any of these transition, here's another thing. In any of these transition metal naming, we're going to know one of the charges by our table. And in this case, that one charge is oxygen. We know oxygen's -2. We know that that means the coppers have to be +2. Since there's 2 coppers now, the previous examples we had only 1 cation. Now that we have 2 coppers, that +2 charge has to be distributed in between both coppers, meaning 1+ for each copper. Therefore, you'd have copper 1 oxide. And if that's the case, what would the next one be? Just CuO. Good, Adi, great job. Copper 2 oxide, because in that case, oh no, in that case, you would have -2 for oxygen still, and then you'd have +2 for copper. And there's only 1 copper to distribute that charge into, so it would have to be +2 for that 1 copper. Any questions about that? About transition metals? No? Okie dokie. Moving on. All right, next, let's switch to covalence. So now covalent, remember I said before we started, the key thing to know is know your compound. So is it ionic or is it covalent? Covalents have non-metals involved, more than one. Ionics have 1 metal and 1 non-metal. So definitely know your bonds. So this one's a bit easier. So what you do is you name the first element. Boom. Then you name the second element as if it were an anion. So that IDE ending is still there. But then you're going to use prefixes for these elements. And there's a rule with prefixes too. And don't worry, at the end I'm going to have a slide that summarizes all the rules. The rule with prefixes is that for the second element, you always have to write a prefix. Always. If there's 1, if there's 2, if there's 100, you always need to write the prefix. For the first element, you don't write it unless there's more than 1. So if there's only 1 of the first element, you don't write the prefix. That's why carbon monoxide is not monocarbon monoxide. Because for the first element, you do not say mono. Every other number above that does apply. So does that make sense? I see people still writing. That's good. Let's do water as an example. So what would water be in this mnemonic, in this naming?
Dihydrogen monoxide.
Good. Dihydrogen monoxide. Good. Dihydrogen monoxide. Because you have 2 hydrogens as the first element. So you write hydrogen, and then there's 2 of them. There's more than 1, so you have to write the prefix. And then for the second element, you always write the prefix. So it would be monoxide. And the next one we went over already, carbon monoxide. And then we went over what's the third one? Carbon dioxide, right. Okay. I felt bad just doing all of them by myself. All right, cool. So any questions on that? And I think the best way for you guys to learn this, practice, practice, practice. The homework is practice. The practice exams are practice. But what I'm going to do also is I'm going to put a non-graded naming practice sheet. You could do it if you want, but I'm going to put it with the answers. I'll put that on Canvas. It's just like, I think 30 or 50 problems, just practicing. So, and since there's only a finite number of these things to name, if you keep naming them, they're bound to come up on the exam. So if you keep doing you can look up online even, you can go beyond that and just look up covalent and ionic naming practice. And you'll get a bunch, you get this worksheets from every school in the country online. So, and you can just do those. but I'll put one up for you on Canvas. Okay, so we went over this already, just naming some of the non-metal anions. You end up with the IDE. And so what you can do is you can write the formula from the name also, so you can go backwards. Oh yeah, so you're on the question, your exam will have periodic table on it. So you'll always be able to access it. I think there'll be a button that says like resources or something, and you click it, and the periodic table comes up on your screen. So you should be able to access that. Okay. So you could also write the name, write the formula from the name, but we can practice that. That's more of practice. Oh, wait, what? Why are the answers there? That sucks. Okay. Damn it. No. Let me see. Let's see if the answers are not there. Wow, the answers are there. That's not good. All right. Close your eyes. Okay, better. Okay, so let's write the formulas of these ionic compounds. And how do I know they're ionic? Oh, look, the first element, they're all metals. So I should give it away. So calcium carbide. So calcium, I know what calcium is. And calcium is 2+. Whenever you're writing these ions, always write their charge. Carbide is carbon as an ion. And it's actually C-4. So what would the formula for calcium carbide be? Anybody? I'll give you a hint. It starts with a C.
Ca2C.
Perfect. Ca2C. Like that. Because of numbers, because your charges have to cancel out. You need 2 calciums to cancel out with 1 carbon. So it would be Ca2C. Like that. Does that make sense? Okay. So now I'm going to give you a minute or two to do the rest 2, 3, and 4 on your own, and I'll go over them in a minute. Okay. So first one, anybody want to give me the answer? Oh, good question. That's a solid good question. So how do we know that carbon is charged 4? Because it's in 4A. So for 4A, we had on the chart that, well, actually it wasn't on the chart. It wasn't on the main chart. But carbon, you might, if you do see carbon as an ion, it's not all the time. It's not common. But if you do, it's going to be -4. Same with silicon. It would be silicide. It's weird though, but you're not going to really see those too much. Good question. All right, so barium nitride, what would that be? Anybody want to give it a shot?
Yeah, Ba3N2.
Perfect. Good. Ba3N2. And the reason is because nitrogen is -3. There's 2 of them, so -6 is the total. And then barium, there's 3 of them, because and then +6 has to be the total. Each one of the bariums is +2. Now, there's an easier rule to do this. It's called the Crisscross Rule. Maybe some of you have heard it from high school. But for barium nitride, it works. For most things, it works. So what you do is you write down the ion, Ba2+, N3-, and what you can simply do is do this. You can crisscross the numbers. And what that does is it gives you Ba3N2. Now that's a rule that's commonly taught. I personally don't like it. Why? Because if you go off this rule for everything, you'll encounter calcium carbide. And for calcium carbide, it doesn't work. Because it doesn't work directly. Because you'll see Ca2+, well, it's right here. You'll see that you would get Ca4C2. That's not reduced enough. That's not correct, actually. If you put that on the test, it's wrong. So the crisscross rule works for most cases. And basically what it is just a fancy way of doing least common multiple. That's really what this is. You're canceling out the negative charges with the positive charges. Okay, next, sodium sulfide, or yeah, sodium phosphide. Anybody want to give it a shot? Good. Na3P. Awesome. Na3P. Reason why, you have phosphorus or phosphide is a -3. Sodium becomes +1. You need 3 of them to cancel out with the -3 from the phosphorus. So you get Na3P. Yeah, the crisscross does work there, right?
What would we do as opposed to crisscross?
Oh, I like the alternative to the crisscross. Okay, so what you would do is just find the least common multiple otherwise. So let's do this. So if you would use logic. I don't know, that's the other way. There's not really method to it. You just kind of use logic. So if you have Na plus and P3 minus, it's Na+1. You just look at them. All right, what's the easiest way for this to go together and negatives to cancel out positives? 3 of sodium. Na3P. Yeah, you guys are all engineers. You have good logic basis. And then alternatively, crisscross rule, you can just do that. Yeah, so Josh, exactly. It's the crisscross rule and make sure the ratio is simplified. That's another way of saying it too. So, yeah. As long as you know how to do it one way or the other. Okay, aluminum sulfide. Anybody want to give this one a shot?
Crisscross, we get Al2S3.
Perfect. Crisscross works. So crisscross works for everything except if it's 2 even numbers. In that case, you might have to reduce the fraction. So Al2S3, perfect, because you have Al, aluminum is 3+, it's in 3A. Sulfur is 2-, and you can just look, what's the least common denominator, least common multiple between them? And if you multiply, if you have 2 aluminums and 3 sulfurs, +6, -6, and that works. Or just do crisscross like that, Al2S3. Like that. Cool.
Couldn't the calcium carbide, the crisscross will work for that if you simplify it?
Exactly, it does, it does. So yeah, it's not like it doesn't work, it always works. But if you're doing it blindly and just, let's say you're learning this quick and you don't really know what you're doing, you get on the test, you do, you're frantic, you do crisscross, all right, C8, 4, C2, that's not right. So you'd have to simplify. So good. All right, cool. So let's move on. That's the same thing. Yeah, cool. All right. Why are the answers there? Oh, that's wrong. Wait, why are the answers there? Okay. Okay. So let's say we want to name TiCl4 up here. Well, whatever, it's there anyway. We know the answer. So you have TiCl4. So you would see in the ionic compound what you know. And you know chlorine. Chlorine is -1. There's 4 of them. This means that the opposite, the titanium, has to be +4. So it would be titanium 4 chloride. We'll do one more. So for lead, it would be lead to bromide for PbBr2. Reason why is because we know bromine is -1. There has to be 2 of them. There is 2 of them. So the lead has to be +2 to cancel it out. So it would be lead to bromide. Cool. Any questions on those, or you got the gist of it? If not, I mean, if you're close and you're like, practice will definitely help. It would definitely help more than me saying the same thing over and over again. Okay, so there are some polyatomic ions. This is going to be the biggest pain in the ass of the next week for you guys, is to try your best to memorize most of these polyatomic ions. And you're looking at me like, what? But it's not that hard. So what a polyatomic ion is, and after this we'll stop for a break. A polyatomic ion is exactly what it sounds like. Polyatomic, more than one atom. Polyatomic ion, more than one atom ion. That's exactly what it is. It's a group of one or group of more than one atoms that itself has an ionic charge. And that ionic charge is just as good as any other ionic charge. And it could be used anywhere. You good? And it can be used in any ionic compound. So you can have sodium acetate. You can have, that's funny. You can have magnesium carbonate, for example. You can have sodium carbonate. You can have any combination of these, mostly anions. They're mostly anions, with any cation. They're just different. They're polyatomic. And there's a bunch of them. So that's the tough part. There's only one of them that's a cation, and that's ammonium. So it's down here. Ammonium is NH4+. So it's like ammonia. Ammonia is NH3. Ammonium is NH4+. But the other ones are not too bad to memorize. So here's how I go through them. I don't know why they don't put phosphate on this list, but whatever. So a lot of them have oxygen. And a lot of them with oxygen have either an ATE, an 8 ending, or an ITE ending, an ite. Usually, or definitely, the ones with the ATE ending have more oxygens than the ones with the ITE ending. So here's let's look at sulfate. So sulfate, SO4 2-. Sulfite, SO3 2-. So it has one less oxygen, and the charge is actually the same. So that'd be a good follow-up question. Professor, why are the charges the same? Well, once we learn about electron configuration, not really the configuration, once we learn about Lewis structure, the Lewis dot structure of these compounds, we'll learn that based on their configuration of the electrons, where they're positioned, it actually ends up being the same charge. And so more in depth, what a polyatomic ion is a group of covalently bounded atoms. Because you can see that all these atoms here are all nonmetals. So if you have more than one nonmetal put together, it's going to be a covalent bond. But the entire covalent bonded entity has its own ionic charge. So you're kind of morphing the two ideas together. You're having a big molecule covalence that itself is ionically charged and can react or make a bond with any other ion. So that's what these things are. And I would say there's videos on how to memorize them. I would say this is the list that is good to memorize. Maybe you could add phosphate on that list. So in terms of memorizing, what you would need to know is the name, the formula, and the charge. Ones that we can get out of the way really quick before we'll take our break is the chlorates. There's 4 chlorates, and they all have a -1 charge, so it's not hard to memorize that. And it goes in levels. So I call it goes like perchlorate is the most amount of oxygens. Just make an artificial thing in your head to just memorize this. So you have perchlorate, which is the biggest chlorate. So chlorate, has, like I said, usually more oxygens. Perchlorate is the maximum amount of oxygen, king of oxygens, ClO4-. Then you have regular chlorate, not as strong as perchlorate, just regular chlorate, ClO3-. Then you have chlorite, which we know the ITEs are weaker than the ATEs. They have less oxygens. So it would be perchlorate, chlorate, chlorite. And then you have baby chlorite, hypochlorite, which is just ClO-. So that's your hierarchy of chlorate to chlorites. That's the way I like to remember it. That's 4 right off the bat. That should be pretty easy to know. Nitrate, nitrite, that's another duo. Sulfate, sulfite. Hydrogen sulfate, hydrogen sulfite, that's another duo. A weird one, chromate and dichromate, because it doesn't really follow the rule. It just kind of CrO4-, and then CrO2O7, 2-. So that's a little bit weird. Hydroxide, we're going to learn a lot about, 8OH-. That's characteristic of bases. So all strong bases have hydroxide in it. Hydrogen carbonate is kind of like carbonate, just with a hydrogen on it. And then you have acetate, easy way to remember that. CHO, like CHO, CHO, 232. That's the way I think of it, at least. Okay, so we're going to take our break here. And, so wait, before that, one more thing. The way you put these into names is you just use their name. It's the easiest thing. So if I were to let's look at acetate, -1 charge. Let's put sodium on it. sodium acetate. That's it. If we did sulfate, sodium sulfate, Na2SO4. That's it. So you don't have to modify these names at all. You just add them on the end if you're dealing with these. And they're just like every other ion besides that. Okay, we'll take our break here. Okay, so polyatomic ions, we'll be working those into our examples. We talked about the chlorates already. All right, so what are the, I don't know why the answers are here, but what are the formulas for the following compounds made of the following ions? So the aluminum ion, the sulfate ion. Now sulfate is SO4 2 minus, and aluminum is Al3 plus. So again, the same things apply that we've been doing. You would use the crisscross rule, that would work completely fine, and you would get Al2 SO4 3. But in this case, when we're dealing with polyatomic ions, if you have more than one of them in your compound, you need to write parentheses around it. So you see parentheses for SO4 3. You can't just write SO4 3 without the parentheses, or else it'll look like SO43. So you need to show that the SO4 is one ionic entity, and that's it. Same thing for chromium 2 with the hydrogen carbonate. So hydrogen carbonate, if we go back, is carbonate, CO3 2 minus, with an added hydrogen. So that would be hydrogen carbonate with it's a -1 charge. So chromium 2 with an anion that's a -1 charge means there has to be 2 of those anions. So 2 of the hydrogen carbonates to cancel out with 1 chromium 2 plus. That's exactly what you do. And your answer would be Cr chromium 2 and then hydrogen carbonate, 2 of those. So that would be in parentheses. So yeah, you would basically apply every rule we learned so far, but just to polyatomic ions like that. Okay, does that make sense? Yeah, I'll give you a minute to write that down. Good. All right. All right. Oh, that makes sense. Okay. So here's some more practice. Write the formulas for the following ionic or covalent compounds. Sorry. So dinitrogen tetroxide. So we didn't go over the exact prefixes yet. We just talked about mono and di and tri maybe, but they're right there for you in number 2. It says mono, di, tri, tetra, penta, hexa, and so forth. So the only ones that might be unique is tetra. Tetra means 4, kind of like Tetris, because every block is like 4.
Pieces have 4 squares.
Exactly. Boom. So yeah, you beat me to it. You want to teach the rest of the class? I could use the rest. Probably. You already have enough extra credit. Oh really? Competition. All right. Whoever wins gets a extra credit. No, whoever wins has to buy me food. Whoever loses has to buy me food. And whoever wins has to buy me food also.
I already got your food.
You already did. All right. Extra credit for everybody. All right. Whatever. Good job. Tetris is. I'm not good at it, so yeah, you probably beat me. So anyway, there's another Tetris player in the chat. Tetris is the best. Yes. I think it's pretty boring actually, but no offense. I'm sorry. But that's because I'm not good at it. Pong. Yes, Pong is fun too. Beer pong. Anyway, I'll take that off of the video. My boss didn't see it. More chats. Okay, we're going to continue with chemistry. So tetra means 4, but every prefix bigger than tetra, you kind of get into the shapes like pentagon, hexagon, heptagon, whatever, so forth. So those should be pretty familiar to most of us. So if you have dinitrogen tetroxide, what should that be? What's the formula? Dinitrogen.
It would be 2 nitrogen, 5 oxygen.
Not 5.
You said 10?
Tetra, first one.
The 4 oxygen.
Yes, 4 oxygens. Good, good. N2O4, exactly. Good. What about sulfur hexafluoride? Anybody in the chat? There we go. Not H6. You put H because of hexa. Yeah, F6. Cool, good. Okay, yeah, so SF6. Good. Diarsenic trisulfide. Arsenic is AS, not AR. AR is arsenic.
S3.
Good. AS2S3. Good. So the covalents, you don't really have to think about it too much. They're a bit easier than the ionics. So, okay, good job. All right, moving on to acids. All right, naming acids. Now, this is a little bit different naming scheme than ionics and covalents, but first we need to define what an acid is. So right now in your bank of knowing how to name things, you have ionic is metal, non-metal, covalent is non-metals. Now we're going to add another one, which is acids, which are technically, well, which are covalent, but they dissociate and they have their own different properties. So an acid is a molecular compound that forms when H plus dissolves in water. In other words, all of these acids are going to have H in the beginning. Acetic acid is H, then acetate. Nitric acid is H, then nitrate. Sulfuric acid is H, H2, then sulfate. So they're acid derivatives by adding H to any of these anions that we just learned. So instead of the cation being a metal, the cation is going to be just H, either one H or two H's, or in phosphoric acid's case, 3 H's, because phosphate is a -3 charge. So let's just, so here's some examples. HCl, hydrochloric acid. H2SO4, sulfuric acid. So anything with an H in the beginning is usually going to be an acid. Okay, so here's how you name them. This looks difficult, but it's not. It's basically, so think of it as hydrogen is now the cation. Now, in order to name it correctly, you need to look at the anion. Does the anion contain oxygen? If the answer is no, then you have to do this, which means, when is the anion going to have O in it? Only when it's polyatomic. Because if it's just oxygen by itself, what's hydrogen and an oxygen put together? It's either hydroxide or it's either water. So when you have an anion that contains oxygen, it's usually, or it's, in this case, it's most definitely a polyatomic ion. Sulfate, carbonate, acetate, nitrate, nitrite, all the chlorites, chlorates, the chlorites, all that stuff we just learned. They all have oxygen in them. So if it doesn't have oxygen, such as if it's just chlorine, just bromine, just phosphorus, just sulfur, then you would do this. You would add the hydro prefix, you would have the root of the anion, and you'd put an IC ending. So for anything that doesn't include oxygen in the anion, you would do this rule. So that includes Cl, HCl, hydrochloric acid. You change the chloride to chloric, hydro in the front. Hydrobromic acid, hydroiodic acid, just to name a few. You have HCN, hydrocyanic acid. Those are just some. Oh, if you have H2S, right? That's hydrosulfuric acid, which is actually different than sulfuric acid. So that's important. Stuff like that is important to mention. Okay. So if you have H2S versus H2SO4. In this case, H2S, it doesn't, the anion does not contain oxygen, it's just sulfur, right? So it would be hydro, because you have the hydro prefix, sulfur, and then you have the IC ending, so sulfuric acid. Now for this one, H2SO4, the anion does have oxygen, it's sulfate. If the anion has oxygen, we check the ending of the anion. If the anion has an ATE ending, just like sulfate, we change the name to ic. So sulfate becomes sulfuric. So it would be, this is called sulfuric acid. So hydrosulfuric acid and sulfuric acid are two completely different things because of this naming scheme. We can tell that. If this naming scheme didn't exist, the names would be the same, but they'd be completely different. Hydrosulfuric acid is a very weak acid, whereas sulfuric acid is the strongest acid there is, conventionally. Here's actually a lot stronger, but for Gen Chem acids, this is the strongest one. Okay, so does that make sense? No? Kind of, maybe. Again, it's one of those things with practice, practice, practice makes perfect. So let's look at the other case. If the anion ends in ITE, we'll use nitrite as an example. Nitrite. So that's, well, nitrite HNO2. If it has an ITE ending, we're going to change the name of the acid to OUS and then add acid. So the name of HNO2 would be nitrous, like nitrous oxide, like Tokyo Drift. Nitrous acid. Like that. That make sense? Yeah, kind of. New rules. You're getting bombarded with a lot of rules.
Did you say like the note taking would decrease all the time?
The note taking? Yeah. Yeah, over time. It's still not over time yet. Give it another 2 weeks. It'll definitely decrease next week because of the test. But yeah, so those are naming acids. I should make a crash count on naming acids. I don't have that. I have it on the acids, but I don't have naming acids. Okay, so here's some common acids. So nitric acid, NO3 is nitrate. The ATE ending becomes IC and then acid. This is nitrous acid, derived from nitrite. The ITE becomes OUS and then acid. And the same thing is the case for sulfate and sulfite. This is phosphate. We didn't see that in the chart. This is PO4 is phosphate. And since it's an ATE, you change it to an IC. It becomes phosphoric acid. Why isn't it phosphic? Why are you directly changing the IC? Because it sounds better. Phosphic is stupid. Phosphoric sounds a lot better. And then you have acetate, ACETATE, and this becomes acetic acid. So you get rid of the ATE and put the IC. So here's just some examples. These are very common ones that we see. Good? Not good? Okay, same thing applies for the chlorites and chlorates. Those are, all right. So we'll do this. Well, let's see some other. Well, we went over hydrosulfuric, chloric, and nitrate. We went over those already. Why are the answers coming out? Okay, so let's name these. So we're already here. We're already here. So let's name these. So HClO2. So now in your bank of knowledge, you should have, all right, if it's metal, non-metal, ionic. If it's a bunch of non-metals, covalent, except if the first thing is a hydrogen, then I have to think twice. It might be an acid. In this case, they're acids. So if anyone remembers, what's the name of ClO2 minus, which is the anion in the first case? What is that anion? So you have chlorite. There's that. Yeah, chlorite. That's what it is. Is that what you said? Or no?
Yeah.
Oh, yeah, okay, yeah. Okay, good, chlorite. So the hierarchy, you have perchlorate, which is ClO4, regular chlorate, ClO3, regular chlorite, ClO2, and then hypochlorite, which is ClO1. So you know it's chlorite. That's ITE. So chlorite. So then what would the acid name be? It ends in ITE. So what would the new name be? It goes to, too late for this, right? Oh, somebody got it in the chat. I feel like I'm putting the people in the room in a more pressure situation. All right, good. Good job, Hal. Good job, Adi. Chlorous acid. Good. So chlorous acid. Good. So the ITE ending changes to OUS. Next one. PO4 is phosphate. Phosphate. Phosphoric acid. Good. Phosphoric acid. Now this one, Br, bromine, it doesn't have a polyatomic ion and it doesn't contain oxygen. So what was the first rule that we talked about for this one? Yep, hydro, good. So when it doesn't have oxygen in it, we use hydro. Bromic, perfect. Hydrobromic acid, good job. I think good job as I'm choking on one of the chips you gave me. So hydrobromic acid. Good. All right, cool. So think about it. Nah, we're good. We don't think about it. But actually, this is an important thing about, but I already said it. How do you know whether a compound is ionic or covalent? Based on what type of atoms in there, metals or non-metals, or both. That's important. All right, so here's the rules. Boom, like Fairly Odd Parents. Okay, now you look up. All right, so yeah, so I have this slide to show you, break down the rules of ionic and covalent bonding. So just so you won't get confused, you can take a picture of it if it helps you study, but it's here for you. So yeah, it goes over all the different rules and really summarizes them well, exactly the rules. Okay. All right, so that's basically everything we went over. All right, so now the last thing actually we're going to do is empirical formula. So, and molecular, wait, what? No? Okay. So some definitions, more notes. So the empirical formula, we kind of already touched on talking about this already. What it is, the simplest ratio of atoms in a compound. So for example, that calcium carbide example, we had Ca2C, or no, if we didn't simplify, it would be Ca4C2. Once we get the empirical formula, it's Ca2C. So it's the simplest ratio. Now, the empirical formula might not always be the molecular formula. In some cases, molecules such as the one written here, C4H10, that's an already defined molecule. It's covalent and it's called butane. So butane has it's a chain of 4 carbons with a bunch of hydrogens attached onto it. It's organic and it burned. You've heard of maybe butane tanks of gas, butane gas. So it's a very flammable organic gas. So butane, that is the structure of the molecule. You can't change that. If you do, it's a different molecule. But it doesn't exist in its empirical formula. it's C4H10. That can easily be reduced to C2H5. So that's just to show you that the molecular formula is not always the same as the empirical formula. And the empirical formula is not always the correct formula for a specific compound. And it's not all the time that the compound always exists in its empirical formula. You might like to think that because, oh, it makes sense that it would exist in its most simplified state. But for molecules, sometimes they bond and make different compounds with even number ratios. It just happens. And butane's a great example of that. And really any of these even numbered organic carbons, hexane, another good example. And then you have the structural formula. Not too important right now. It's just the order of arrangement of the compound. So yeah, we know the empirical formula, the simplest whole number ratio. And what we're going to do, the main skill we're going to learn, is how to calculate and determine the empirical formula from a question. So finding the formula, there's 4 steps. Is there a question? Oh, can I go back? Yeah, sure. Yeah, so you don't need to write everything, but you can if you want.
I'm good.
Oh, you're good? Okay, cool. All right, so there's 4 main steps to finding the empirical formula. The first is the kind of questions you're going to be given, just to give you a preface. They're going to have some compound has this percentage of carbon, this percentage of hydrogen, and this percentage of oxygen. What's the empirical formula? And what's the molecular formula if the molecular mass is 120, something like that. So what you're going to do is you want to convert given percentages and pretend those percentages are in a sample size of 100 grams and convert them to grams. So if it's like, oh, the random sample is 50% hydrogen, 50% carbon, you can turn that into 50 grams of hydrogen, 50 grams of carbon, and pretend it's a 100-gram sample. This is just to make it simpler for you when you do step 2, which is converting those new gram values into moles, which we know how to do. We can convert those by dividing by the molar mass of those compounds, or of those elements. Then the third step is, at this point, you're going to have 2 or 3 or 4 mole quantities in that 100-gram sample of each of the elements in these compounds, in the compound you're looking for the empirical formula for. So your job is to then divide by the least amount of moles, basically reducing this number. So you're reducing it to its simplest whole number mole ratio. That's exactly what you're doing by dividing it by the lowest number. So that simple number, that simple mole ratio, the simplified mole ratio, is basically the empirical formula. And then from there, you may, and you probably will, because we like to trick you, is you need to multiply all the mole ratios by a number to make all the numbers whole numbers. Because after step 3, you might end up with, oh, it's 1 mole of hydrogen to 1 mole of carbon to 1.5 moles of oxygen. And you know you can't put 1.5 in a formula. So you'd have to multiply the entire thing by 2. Exactly. So your empirical formula would then be H2C2O3, based on what I just said. But the best way to learn this is by doing examples. So we're going to do an example right now. All right, so you have 100 grams of a substance, contains 38.6, we'll just get out of this, 38.67. Damn it, I hate it. All right, we'll just do it on a different slide. All right, so we have 100 grams of a substance, and it contains 38.67 grams of carbon. It contains 16.22 grams of hydrogen, and it contains 45.11 grams of nitrogen. Now, this question did the simplifying for you or did the converting from percentages to grams for you. So you don't have to worry about making it out of a 100-gram sample. If they're already in grams, you go from there. So the first step is we are dividing by the molar masses of each of these elements. So we're dividing by 12 here. That gives us a number. We're dividing by 1 here, or 1.008, or put 12.01 there, 1.008, and dividing nitrogen by 14, which is the molar mass. And then you get 3.33 moles of carbon, 16.09 moles of hydrogen, and 3.22 moles of nitrogen. Does that part make sense? How we got those numbers? Good? Okay, so we just found the moles. Now we're going to divide by the lowest number of moles. Divide all the numbers by the lowest number of moles. Is there a chem group chat? GC, I assume it means group chat. And yes, there is. Can someone drop the link for her? I don't have it. You guys excluded me. No, I told you to exclude me. That'd be weird if I was in it. And I have enough group chats. I don't want to bother. All right. So nitrogen. So nitrogen has the lowest number of moles, 3.22. So we're going to divide all these numbers by 3.22. So now the new carbon ratio, the simplified mole ratio, is 3.33 divided by 3.22, which is equal to, I don't know, about 1 point something,
1.034.
Okay, cool. 1.03, good enough. Next one, hydrogen. So you're going to have 16.09 divided by 3.22, and that should equal around 5. But what is it exactly?
4.99.
Good, 4.99. And then oxygen, oh no, nitrogen is just going to be 1. It's 3.22 divided by 3.22, it's going to be 1. Okay, so this part's important because when you do these calculations, it's easy for me to say it, and then when you guys do it, you might have different experiences. So that's why we're doing this together. You might see numbers like this. It's not exactly 1, it's not exactly 5, but it's really damn close. So if it's really damn close, then you can round it to that whole number. Even though you're looking for simplified whole numbers, if it's that close, you can round it. So if it's something like 1.1, that's not close enough. So maybe you did something wrong, maybe you want to go back. If it's something like 1.25, 1.33, 1.5, numbers like, or even 1.75, numbers like that gives you an indicator that you might need to multiply the entire ratio by a whole number in order to make all of those numbers whole. So like 1.25, you multiply the whole thing by 4. 1.33, you multiply the whole thing by 3. 1.5, you multiply the whole thing by 2. 0.75, what do you multiply by 3? Yeah, you multiply by 3.
Yeah, I got 3.22 for the moles of carbon.
Oh, you got that. Oh, did I misread it? Huh. It's in the work up here. It says 3.33.
I don't know.
Yeah. Whatever. Idea is it's close enough. So anyway, tomato. So anyway, once you're done, this simplified molar ratio gives you your answer, and you get C1 or just C, H5N1. That would be CH5N. So that would be your empirical formula. So does that make sense? We're going to do another one, but does that make sense?
Yeah.
Kind of. All right. So it's just the process, and there is questions on the homework about it. So, all right, here's another one. So we have a laboratory analysis of aspirin. Determine the molecular formula by mass percent. So the mass percent of carbon is 60%. Let's convert that directly to 60 grams. Hydrogen, 4.47. So make it 4.47 grams. Oxygen, 35.53 grams. And the question is, find the empirical formula. So let's do that. So we're going to divide carbon, the carbon grams, by its molecular mass, which is 12.01, and you should get very, very close to 5, with 5 moles. Then we're going to divide 4.47 grams divided by 1.008, and what do you get? 4 point something, right? .47 divided by 1.008, 4.43. And then we're taking 35.53 grams of oxygen, dividing it by 16. So 35.53 divided by 16, 2.22. 2.22 moles of oxygen. Okay, so now what we're going to do, and I'll do that work down here. So what we're going to do is we're going to divide by the lowest number of moles to simplify this molar ratio into whole numbers. So that's clearly oxygen. So for carbon, it will be 5 divided by 2.22, which is going to equal 2.25. That should give you a hint on what we're going to have to do. So 2.25 moles of carbon. For hydrogen, we're going to do 4.43 divided by 2.22, and that's going to be almost exactly 2. So 4.43 divided by 2.22 equals 1.995 moles of hydrogen, and you get 1 mole of oxygen. 1 mole of oxygen because you're dividing the 2.22 by itself. Okay, so now we have approximately 2 moles of hydrogen, 1 mole of oxygen, and 2.25 moles of carbon. So anyone want to tell me what would we do now? Good. Multiply the entire ratio by 4. So right now the ratio is 2.25 to 2 to 1. We're going to multiply everything by 4. So 2.25 times 4 is 9. I knew that. I just wanted to check it because it's late. So it would be C9, and then multiplying 2 times 4, H8, and then multiplying 1 times 4, 4, O4. So there is your empirical formula for aspirin. And that's also the molecular formula for aspirin, in case you're wondering. Cool. So does that make sense? Is that make it more clear? Hopefully so. Good, good. Okay. Cool. And you, boom, you do the math, and you get the answer. Cool. All right, so we talked about structural formula and empirical formula. Now, in some cases, you might want to do the empirical formula, and it may ask a follow-up question of what's the molecular formula if it gives you another piece of information. And what you know is that the molecular formula is a ratio, or is a multiple of the empirical formula, right? So in some cases, well, in every case, the molecular formula is going to be the empirical formula molar mass times some constant, 1, 2, 3, 4. So there could be examples where we could figure that out. So here's an example. Let's say the empirical formula for compound X is C2H3O. That's the empirical formula. We did all the math already. We figured that out. The question is saying the molar mass, or if the molar mass is 86.03, what's the formula for the molecular formula? Or what's the molecular formula? Oh, and it has a name. Butadiene. Glutathione. Yeah. Okay. So you have the empirical formula and you have the molar mass, meaning the molecular formula's mass. So now the way to do this is figure out the molar mass of the empirical formula. That molar mass is 1 unit of the of the total molar mass of the molecular formula. Sorry. So you want to see how many times that empirical formula fits into the molecular formula by mass. So that's easy to figure out the molar mass of this. C2 would be 24, H3 would be 3, and O would be 16. 27 plus 16 is what, 43? Yeah, 43. So then you would do 86, which is the total molar mass, divided by 43, which they did right here. And you get 2. 2 is not your answer. 2 is the amount of times the empirical formula fits into the molecular formula. So what that means is multiply the entire empirical formula by 2. And you end up with C4H6O2, like that. I'll give you a couple seconds to write that. Any questions on that? No? Okay, moving along. Oh, there's a question. How do you know, and if you don't know, empirical form molar mass? Oh, so I think that's what you said. So if you know the empirical formula, you can figure out the empirical formula molar mass by calculating it. So you have C2H3O. When it gives you the molar mass of the compound, that means the molecular formula, the whole thing, not the empirical formula mass. The empirical formula mass, it won't give you because you can just calculate it. So you get the 43, and then you divide it by the molar mass, and then you get the factor of multiplicity of the empirical formula into the molecular formula. Factor of multiplicity. That sounds complicated. It just means how many times something goes into something. Anyway, so hopefully that answered your question. Now, combustion. So we're going to do, and this is probably the type that's going to be on the exam, so it's important to pay attention. This is one of the last things we're going to do today. So a combustion reaction is a definition. It means you're taking an organic compound. Organic means it has C's and H's. It could have O's in it too, and nitrogens also. But mostly it's going to have C's and H's. And then you're going to add oxygen, because oxygen is fire. You need oxygen to fuel the fire. And then what's going to be released is heat. And the two most important things are all the time it's going to be CO2 and H2O. That's what the definition of combustion is. It's an organic compound, C's and H's, adding oxygen, making CO2 and H2O. It happens with, this is combustion of methane, could be hexane, butane, decane, whatever. The key thing, when we're going to be figuring out the empirical formula of something that we're burning from this, combusting. And the way we're going to do that is by using the facts of the equation. As if we look at the products, right, CO2 and H2O, we see that carbon is only present in CO2. And that's the only place in the products where carbon is. So we can say, we can narrow down carbon to there. And we'll use this information in the example that we do. Oxygen's in both places, carbon and water. So, or the CO2 and the water. So ignore that. Hydrogen is only in the water. So we have one of these products only has hydrogen. The other one only has carbon. And the remainder of that mass is oxygen. So that's the kind of approach we're going to be using when solving these problems. Is we're going to kind of break it down, figure out what we can figure out in terms of percent hydrogen, percent carbon, and the remainder is going to be percent oxygen. And from there, we can figure out, do the same empirical formula steps. All right, so let's just get to the thing. Here we go. So a certain carboxylic acid, and we'll split screen this. All right, so we will minimize that. Okay. Cool. All right, so a certain carboxylic acid contains hydrogen, carbon, and nitrogen. Carbon, hydrogen, oxygen, and nitrogen. Combustion of 2.175 grams of the compound produces 3.94 grams of CO2. So you can write this information down. So 3.94 grams of CO2, 1.88 grams of H2O, and that's it. In a separate experiment, 1.873 grams of the compound was found to contain 0.359 grams of nitrogen. Okay, so we know that the ratio of the percent of nitrogen is 0.359 grams to 1.873 grams. That's the percent. So total, and then percent nitrogen. Okay, so using all this information, we should be able to figure out what the compound is. So, and also they give you a scheme of how to do it. So let's figure out the moles of carbon in the sample. So moles of carbon in the sample. We're going to take the grams of carbon dioxide. We're going to divide it by the molar mass. So divide by 44. And we're going to get 3.7 divided by 44. You get 0.89 moles of CO2, right? And then that equates to 0.89 moles of carbon. Good. Next, we have the 1.88 grams of H2O. So we can just divide that by 18, just like we did before, and we'll get 1.88 divided by 18, 0.104 moles of H2O, which equal 0.208 moles of hydrogen. Okay, so let's look at, we already knocked out the first four problems from here. So you see moles of carbon in the sample compound, 0.89. Mass of carbon in the sample compound. Multiply 0.89 by 12.01. You get the mass in grams of carbon. Moles of hydrogen in the sample. Well, we look at the water component of the production by combustion, and we get 0.208. The mass is 0.208 times 1.008, which is the molar mass of water, and you get whatever that is. Now, the mass of nitrogen, is the question. What's the 44? 44 is the molar mass of CO2. Sorry I did that part a little bit fast because I repeated it from the last problem. So now, mass of nitrogen in 2.175 grams of the sample. Because if you remember, the original sample was 2.175. But that second experiment they did gave us the percent nitrogen in the compound, which we can calculate right now by doing the 0.359 divided by 1.873. And we get 0.192, or 19.2% nitrogen. So the question's asking for, out of the 2.175 gram sample, how much nitrogen do we have? So we take 2.175 multiplied by our percent 0.192 of nitrogen, and we get 0.42 grams of nitrogen. I'll put in sample, Okay, I did a lot of math right now. Does everybody follow? And if not, please ask questions. I did go through that kind of fast. So I figured it's good that they give you the scheme of how to do it because you can get lost. But basically, I'm using the components of the combustion reaction to figure out the carbon component, then the hydrogen component, then the nitrogen component, and then we can figure out the oxygen component from all of that information. Oh, I messed up. Yeah, Josh, you're right. I messed up. So, it's not a good night. 0.394 divided by 44. Or sorry, 3.94 divided by 44. I forgot a 0. So it's 0.0, so point should be there, 0.089. Thanks, Josh. Thanks so much. So 0.089. And everything else is correct. Yes. Okay. Thank you. Okay, so now we have 3 out of the 4 components. We have the masses of them. So the way to figure out the mass of oxygen is just simply subtract the masses of the other 3 by the total sample, which is the 2.175. So it would be 2.175 minus the mass of carbon, which would be the moles of carbon, 0.089 times 12, which is 1.07, minus the moles of hydrogen. Moles of hydrogen is about, or sorry, the grams of hydrogen, which is about 0.2. And then the grams of nitrogen, 0.42. So you do that math, and you end up with 2.175 minus 1.07 minus 0.2 minus 0.42. You end up with 0.485 grams of oxygen. Okay, good. So now, what can you do? You have everything. So you can figure out the moles of oxygen because you know the moles of everything else. You can figure out the moles of everything. We're going to finish this problem. So here, I'll do this. I'll move this over. Okay. All right. So hopefully that makes sense. All right. So now, what we can do is remember empirical formula. The goal is to figure out the moles of every component and then divide by the least number, right? So we have the moles of carbon, which is 0.089 carbon. We have the hydrogen, 0.208 hydrogen. We have the nitrogen, which is just finding the moles that's in 0.42. So 0.42 divided by 14, you get 0.03 nitrogen. Right? Yeah. 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 Then you have the oxygen, 0.485 divided by 16 is 0.03 again of oxygen. Okay, so does that make sense? I know it's a lot. I know we kind of went through this. It's late. So does that make sense? Yeah, kind of. All right, so now the rest of it is repetitive from what we did last time. So we're going to divide by the lowest number. So we divide by 0.03 moles. So that means our nitrogen number would be 1. Our oxygen number would be 1. Our hydrogen number would be 0.208 divided by 0.03, which is actually 6.93. 6.93. That's close enough to 7, by the way. And then you have your 0.089 for your carbon divided by the lowest number, 0.03, and that is 2.97. Awesome, 2.97. So then this is about 3, close enough to 3, close enough to 7. You have C3H7NO. And that is your empirical formula for this question. So that is as hard as it's going to get on the test. You're probably going to see one of these on the test. Yes. So that's why doing this one again, and also the other practice test that I did post has another one of these. And I think the homework has one too. Maybe. I'm not sure. But definitely check that out. And what I'm going to do, since this is a laborious process, I'm going to make a small video. I'm just going over this, and I'll put it on Canvas. It's going, not this exact one, but another one, just so you have the process down in I'll do it in 5 minutes, so you don't have to scroll through this video for 2 hours and find it. Okay, Josh said on the homework it says don't round until the end, and sig figs was that the test. Yeah, don't round till the end. Don't worry about sig figs on the test. Don't worry, just unless it says so. Unless it says how many sig figs are in the number. So if you're doing a question like this, where it's really intense, keep your numbers as precise as possible until the end, because you're doing so many calculation steps. You could, at the end of the day, if you do sig figs, you could be off by a whole unit. In that case, it's not good. So don't round to the end. Follow the homework directions for the test. Unless it says round this number to the nearest sig figs or something, or to 3 sig figs. Okay, now there's a follow-up question. If the molar mass of the compound is 146, what is the molecular formula? So let's take the empirical formula, which is this, and we'll see how many times it goes into the molecular formula. So 12 times 3 is 36, plus 7 for hydrogen, plus 14 for nitrogen, plus 16 for oxygen. And the empirical mass is 73. So 146 is 2 times 73. So you know that the molecular formula is C6H14 and 2O2, like that. Okay, cool. Is there any questions on that? Because we should move on because we're almost done with class. No? All right, good. The rest of it is smooth sailing, very easy stuff compared to this. Oh, there is a question online. Hold on. Can you explain how to determine the order of the letters? You mean like the carbon, nitrogen? Oh, the order of the letters in the formula. It doesn't matter, but usually, and this is actually not right. So usually it goes CHON, C-H-O-N is how you would write it for organic compounds. But as long as the carbon and hydrogen are, it's usually carbon, hydrogen, CH, and then everything else follows. So that's a good rule of thumb. And then for acids, the H is always in the front. So you need to have an H in the front. Okay, so, all right, molar masses, we know how to do that already. Molar mass, we know how to do that. So now something that we're going to learn is mass percent. So which is, we basically know how to do that already. But if you were to figure out how many grams of oxygen are present in 1 mole of iron 3 oxide, how would we do that? So we need to figure out what iron 3 oxide is. And we know that from all of our naming, right? So that seems like it was so long ago we did naming, but it's like an hour, less than an hour. I guess an hour. So we have iron 3 oxide. So iron 3 is Fe3 plus, oxygen is O2 minus. You could do crisscross rule, whatever. You get Fe2O3. So then figure out how many grams of oxygen are present in 1 mole. You figure out 3 times the molar mass of oxygen is 48, and you're done. So that's 48 grams. I know I went through that quick, but does that make sense? Okay. And then the last thing is, we went over these kind of stoichiometric things where like how many molecules are in 50 grams of PbO2. Basically, you find the moles, and then you find the molecules from there. You're using Avogadro's number. We did that, right? Yeah? Okay, cool. All right. I'll have to go over that again. And then mass percent. We'll just do some, we'll just do some very similar to what we just did with the iron 3 oxide. But we'll do a quick example. So calculate the mass percent of oxygen in, what is this called? Anybody want to tell me what that's called? First of all, is it ionic or covalent?
Ionic.
Good, because it has the Na, which is sodium, which is a metal. Now, what is it called?
Sodium perchlorate.
Perfect. Sodium perchlorate, and somebody online almost beat you, but it's actually perchlorate, Josh. Because perchlorate, close, it was close though, good job. So perchlorate is the highest level of chlorate. It has the 4 oxygens. It goes perchlorate, chlorate, chlorite, hypochlorite. So in the sodium perchlorate, we need to figure out the total molar mass. Sodium is 23, chlorine is 35.45, and an oxygen would be 4 times 16. So 4 times 16 is 64, plus 23, plus 35.45, and you get 122.45. It's asking for the mass percent of oxygen. So what percentage of this 122 is oxygen? This is oxygen, so that means 64 divided by 122.45. That's to be about a little bit more than half. So I think the answer is 52.3. And that's correct. Cool. So that's just mass percent. If you know how to do empirical formula, your mass percent is very easy. Or at least it should be. So any questions on that? No? Okay, cool. So that's basically it. We've done this, we've done that skill already. That's a good one. Oh, I just told you the answers. Would you define what the greater mass percent of oxygen? H2O or H2O2? Greater mass percent of oxygen. H2O2. It's got double the oxygen. Even if it had 4 times the hydrogen but double the oxygen, it would still be the oxygen because each oxygen is 16. So you're adding a lot more. What about the next one? Greater mass percent of oxygen. A or B? First one or the second one? 1 or 2? Yeah, it's not a trick question. You're right. It's 2. Yeah. I looked at that too. I'm like, that's too easy. Wow. Okay. So yeah, greater mass percent of oxygen. You're going to have more oxygens. Everything else is the same. So it'll be the greater mass percent. Okay. So that's enough of me. That's it. So I'm going to end the recording, and we're done.